Okay, so I think if we look at the developments of machine learning over the last 40 years, I think it's safe to say that our focus has been on just making it work, right? Can we do anything with these systems at all? And that means that we focused on accuracy, speed, and scaling, mostly on accuracy. And this means we've largely ignored other engineering concerns, including all of the illities, right? Testability, reliability, safety, evolvability, maintainability. But now we're seeing that AI techniques and machine learning techniques are being incorporated into high stakes applications. And all of these now come to the forefront as important issues for us. And so in this talk today, I'm going to focus on primarily on robustness. Does this do the right thing? No. And see basically what kinds of ideas we have in AI and machine learning to make systems more robust. So in particular, I'm going to look at two areas of robustness. The first is robustness against the known unknowns. That is, as Claire was describing in her talk, there are some set of variables that we're modeling. We have a model of their relationships, and this is also on auto advance. Okay, guys, you fail, and I guess my mouse is somewhere off screen. Here, okay, slideshow. Don't use timings. Oops, that's not mine. Okay, and you're not even using my PowerPoint version at all either, are you? No. Where is it? Or not? Well, as several people have suggested, the challenge of computer science is not AI, it's just getting the projector to work. Okay. Okay, yeah. So just, no? No? Oh, I see. Okay. Okay, so two dimensions of risk, there are robustness. Robustness to modeled phenomena and then robustness to unmodeled phenomena. So let's start with the basic idea of robust optimization, which Claire was also hinting at. If we consider something like a linear programming problem, right, imagine we just have two inequality constraints down here at the bottom, and our objective function j is increasing upward and to the right. And so we know that our linear programming algorithms can find the solution. But what if we're uncertain about A, B, C, D, and R and S? So we have uncertainty about our constraints. Or we could also look at uncertainty in our objective function as well. Well, in that case, what we can do is define uncertainty regions around those variables. And then we can imagine, and that lets us model the fact that there's really a whole set of possible linear programs, and we're not sure exactly which one we're solving. Now, what we can do is minimax against that uncertainty. So we can allow an adversary to change the values of those variables within those uncertainty regions and see, well, what can we achieve? So the adversary gets to try to minimize these variables, A, B, C, D, R, and S, minimize the objective with respect to those variables, and we're trying to maximize it. But the problem with this approach is it tends to be very conservative. We know that the solution set in a linear program is a big polytope, and there are a lot of corners, and those corners could be really extreme in this case. So a standard approach, and I think this was introduced by Dimitri Boutsimas at MIT, is to put a budget on the adversary. So now the adversary is allowed to perturb A, B, C, D, R, and S by some amounts, delta A, delta B, and so on. And the sum of all of those perturbations, the sum of the delta i's, has to be less than some budget B. And so now we can vary B. If we set B to 0, we get back the original problem and the original value of the objective. And as we make B larger, we're allowing our adversary to do more and more damage to us, and we can see what the consequences of that are for our performance. So that's the basic idea of robust optimization. Well, it turns out that some of the algorithms we have in machine learning are already doing some form of robust optimization. We just didn't realize that. And in this case, this is work coming out of Shimon Orr's lab at the Technion. And what they showed was that for the standard support vector machine objective, which is this one here, that we can view it as a form of robust optimization. So in the standard support vector machine formulation, we have training examples, xi, yi, from some unknown function, y equals f of x, and we're given a loss function that tells us how bad is it to predict y hat when the right answer was y. And then we try to find a model that minimizes the sum of our losses on our predictions on each data point, plus this other term which we think of in machine learning as a complexity penalty, sort of enforcing Occam's razor. We prefer simpler models. And we have this parameter lambda, which is always this magic parameter. We usually fit it by using cross-validation techniques. And it's letting us trade things off. So if we set lambda to 0, then we're just trying to fit the data, and we'll tend to overfit the data as a result. If we make lambda very, very big, then maybe we almost ignore the data because we're just trying to use like the all zero function in order to keep that penalty small. So it turns out that Xu, Karamanos, and Manor showed that under a particular setup here, that lambda is actually a budget on an adversary who's allowed to perturb each of your data points by a certain amount. And if you're using the Euclidean norm on the perturbations, then you get the Euclidean norm on the deltas, and so on. So it's a beautiful thing, and it kind of makes sense that, in fact, Manor and his students have a proof that for a large class of learning problems, this is actually necessary and sufficient to get generalization, is that you have to be robust to your data points moving around. That's essentially the definition of generalization. But the nice thing about this is it also tells us what is this lambda parameter. It's actually the freedom of action we're giving to our adversary. Well, they've found a similar result for sequential decision-making problems, like the reinforcement learning problems or the air traffic control problems we were just discussing, where at each time step, our controller observes the state of the system, xt, and then it chooses a control action, ut, according to some control policy, which is called pi conventionally. And then it receives a stream of rewards at each time step. And the system is going from one state to another, and we want to find the policy that optimizes the total reward. Well, there's been a lot of interest. You know, if you pick up the standard AI textbook or almost any paper in machine learning, they'll say, well, our goal is to maximize the expected return. And so we think about the expected value of a lot of things. But suppose we're in a situation where we're worried about downside risk. If we look at a particular control policy, and we run it many, many times, we'll experience different amounts of reward because of the randomness, the stochasticity, the noise, or disturbances in the system. And so there will be some probability distribution of our returns. And in this case, suppose the distribution looks like this, that most of the time we get a nice high return, somewhere around 6 or 7. But sometimes we have we might end up in that left tail where we have very bad returns. And so in finance, they've developed this objective they call the conditional value at risk. And the idea is that we just look at the 10% worst outcomes and their expected value. Okay, and so the conditional value at risk here at the 10% quantile is 3.06. And so Manor and his students developed algorithms for optimizing that conditional value at risk. So what is the control policy that would make that downside risk as low as possible? And it looks something like, does something typically like this. That is, it can shift the reward curve on the left tail upwards, so that we have a lower downside risk, but we often lose something on the upside too, right? So the upside shifts in. Well, it turns out that this they've shown is equivalent to an adversary that is allowed to change the transition probabilities of the dynamics of the system by multiplying each of the transitions in the model by some amount delta t, such that the product of all those deltas is 1 divided by alpha, which was the quantile we're interested in. So if we have the expected value if we set alpha to 1, so we're back to just the full expected value, then all of these deltas have to be 1s. The adversary can't do anything. But if we let the adversary really make big changes in our transitions, then that's equivalent to delta getting very small and giving the adversary a big budget. So this tells us that acting conservatively gives us robustness to an adversary, which is an interesting thing that I think we all expected was true, but it's nice to see it confirmed. And so I think the lesson for us is that we can build AI systems so that they will act conservatively and try to avoid catastrophes if we have models of them. Okay, there's similar things can be done in probabilistic inference, but I don't have time to talk about that. So let me talk about unmodeled phenomena, because I think this is really where things get fascinating intellectually, right? Any system that we field will have an incomplete model of the world, and the question is, how can it behave well even when its model is wrong? And Claire also addressed this, right, in her learning where the initial model of the safety region is incorrect. So one approach, which is what she was doing in her work, is to have a system that can detect its model failures. In its case, it thought it was going to stay inside a region, but it turned out it actually left that region. And it says, whoa, my model of my dynamics is wrong. I'm going to constrict the safety region so that, to add a margin of safety. It doesn't really know why the model is wrong, but it's being conservative. But another thing it could do is actually formulate and solve learning tasks to try to expand the model. And Claire's system is doing that too. It starts to experiment and explore a little bit so that it learns a much better model of the problem. In practice, in most of the applications I'm familiar with, it's the humans that do this step. And there's also a risk, of course, that every new fact we add to the model actually has some error in it. And if we add a lot of those, then we'll end up with a model that's got more and more errors. Another idea that we have in machine learning is to try to learn causal models rather than purely correlational models. This requires typically the ability to do randomized experiments, but more and more, particularly in the online world, we can do that. And so we can start to think about learning causal models. And their advantage is that we can transport them from the data that we use to learn them to very different places. I mean, the most extreme example of this, I think, is in physics. We have causal models that are so good that we can predict what's happening inside the sun or in black holes, even though we've never been able to get any instruments to those places. The seventh idea we have is ensembles or portfolios, right? So if there's a high risk using a single model, if we use a portfolio or ensemble of models, we can often do better. And these completely rule the roost in machine learning methods. But I wanted to give an example from some other part of AI, which is satisfiability solvers. So one example of a portfolio method is SatZilla, which is a system that combines several different, so it turns out, of course, in the satisfiability literature, there are a wide variety of different satisfiability solving algorithms. And depending on which problem you're trying to solve, some of those algorithms will be much better than others, and quite dramatically better in some cases. And so there are these competitions that are run where there's a whole collection of satisfiability problems, and the goal is to try to choose the best solver for each one. And the black line is an oracle that cheats and knows the answer, and what it's plotting is the percent of problem instances solved within 1,000 seconds, which is the budget you have. The dotted lines are individual solvers and how well they do, and this red line is their portfolio, which you can see is able to almost match the quality of the oracle, solving something well over 90% of the problem instances under the deadline. And I think we have this kind of ensembling showing up in other systems like Watson and the Google and Bing search engines essentially have a variety of different subsystems, which we can think of as solvers for questions, and the answers from those are combined and ranked. And there's even knowledge level redundancy where we would like to have a system that can look at a problem from more than one perspective. And I would say right now most of our machine learning systems only have a sort of single view of a problem. So for instance, there's been a lot of work in image labeling, right, where system writes a caption to describe an image. And what that's essentially doing is just predicting what sentence would a person write when looking at this image. But we'd really like to be able to have other facets. For instance, the ownership facet, that there's probably a person that owns the cat, the book, and the chair. The goal facet is that the person might want to read the book. the person might want to sit on the chair, and so on. And we might be able to use those to predict things like the cat's not going to be there very long. But right now, our systems only view this in one facet. And so I think to achieve this kind of robust, multifaceted understanding, our systems need a much wider variety of experiences about the world. And that comes back to the point from the previous panel about the need to collect much more data about many different facets of the world. The last thing we can do is monitor for anomalies. And I'm running out of time, but I'll just say that some of the work that we're doing at Oregon State, this is with Alan Fern, is to try to put an anomaly detector in series with a learned function classifier. So that when a query comes in, we can ask, is this query anomalous compared to the training data that we were trained on? And if it is anomalous, then we should probably reject it and ask for help or take some safe action in response, as opposed to trusting our classifier. And this really addresses a question that came up in the QA session the last time. So just to wrap up then, the recent success in AI is leading us to want to put AI into high stakes applications like self-driving cars and so forth. And that requires that we start addressing the illities. One of those illities is reliability or robustness. And we do have some ideas about how to do that. I think we could use more ideas. But I think all of these ideas, methods, tend to cause AI systems to act more cautiously. They give the system some awareness, quote unquote, of their own limitations. They don't trust their models. They're constantly checking them to see if those models are correct. And they're also planning under the assumption that there's some incorrectness in their models. And I'll stop there.